Hi everyone, I'm Xiaoling Wang. I'm from Northwestern Polytechnical University in China. It's my great honor to attend this meeting. Today, I will introduce my paper, Rapid Chain Prediction for Large-Scale Cloud Database KPIs by Clustering. There are 4 parts in my presentation. There are backgrounds, trend prediction based on clustering, experiment and analysis, conclusions. According to Gartner's report, 75% of all databases will be deployed or migrated to a cloud platform by 2022. So, cloud database maintenance is an essential task. We study trend prediction because for cloud database product, flexible scalability is one of the most attractive features. If the KPIs chain can be predicted several days or weeks in advance, operation and maintenance team will adjust cloud resources timely and then reduce the cost of operation and maintenance. For KPIs prediction, there are few trend prediction methods. As we know, the only KPI prediction method is AutoPA4DB. AutoPA4DB is applied for each KPI, while there are large-scale monitored KPIs from cloud database maintenance. So this method results in massive resource and time consumption for model selection, parameter tuning, and training. Luckily, many KPIs are similar, so we cluster KPIs based on similar shape. So we only need to predict a few KPIs. In existing time series clustering method, ROCKA can obtain good performance. ROCKA clusters based on dbScan. dbScan is a density-based algorithm. The main idea of dbScan is to find some calls in dense regions and then expand the calls by transitivity of similarity to form clusters. The left figure is the clustering process. The left figure is an density-based clustering example. The right figure is the clustering process. As we can see, density-based clustering performance based on density radius. ROCKA proposed a density radius estimation method. K-distance is the distance between an object and its k-nearest number. Like this figure, ROCKA believes that a flat portion of a k-distance curve indicates the density around the number of objects is consistent, while a steep part shows significant density changes. So k-distance, a flat part of this curve, can be considered as candidates, since it ensures a good number of calls to expand clusters. The algorithm is as this figure for each point. If its flat left slope or right slope is small enough, and slope difference is small enough, then this might add this point into candidates. Lastly, choose maximum from candidates at the best density radius. Although the flat part is obvious in this figure, but when considering an example from the public dataset, as figure 1, it's not easy to discriminate between the flat part and the steep part. So according to this finding, we hope that we can find a method which can discriminate between the flat part and the steep part. Now we will introduce our work, a rapid KPI trend prediction framework. It's a trend prediction based on clustering. The ideal TPC is as follows. Firstly, pre-processing original historical KPIs. Then clustering KPIs based on shape similarity of KPIs with improved ROCKA. After that, we can extract each cluster centroid. For each clustering centroid, training trend prediction model and tuning parameters with auto PA4DB. When predicting a new KPI, classifying it into the nearest cluster, then predicting trend with its centroid model. Because of ROCKA's weak point, we improve the ROCKA. The improved ROCKA is as figure 3. Firstly, obtain the density radius by algorithm 1 and algorithm 2, then clustering with the dB scale. After clustering, we can get cluster centroid. The right figure is an experiment example of cluster centroid. The red part is the cluster centroid. The black part is other KPI. We can see that the cluster centroid represents the cluster feature. We use algorithm 1 of ROCKA to find all candidates. But ROCKA performs not well on complicated KPIs because of poor density radius. So we find some best density radius by algorithm 2. After obtaining all candidates, we obtain k-distance curve of candidates. The turning point can discriminate between the flat part and the steep part. In algorithm 2, we find turning point by finding the cosine maximum between vector PF and vector PO. Then we cluster all candidates with dB scale, where EPS equals k-distance of turning point. Lastly, we choose the maximum in cluster which has most candidates. With improved ROCKA, we cluster KPIs and obtain cluster centroid. Then we build models with auto PA4DB and get optimal trend prediction model for cluster centroid. For experiment, we use two kinds of dataset. The first is the public UCR dataset. UCR is the widely used time series dataset with class labels. In order to compare with ROCKA, we also use three datasets in UCR. They all have large size and high dimensionality. They are considered as idealized data with very few noises and outliers. However, time series streams in UCR are not KPIs, so we only use them in clustering performance comparison. The other two datasets are real-world industrial datasets from large companies. DS1 has 16 KPIs from 6 cloud database instances. Each database instance has 10 KPIs. Besides DS1, we also use another DS2 published in a competition. DS2 has 6 KPIs. For clustering, we use KNMI to compare the accuracy. It ranges from 0 to 1, while 1 means the clusters perfectly match the labels, and 0 indicates they are completely irrelevant. Another clustering metric is F-score. F-score refers to a harmonic mean of precision and record, and it ranges from 0 to 1. F-score has its best value at 1 and worst at 0. F-score is calculated both based on the confusion metrics such as type A in Table 3. For multi-cluster case, we need to calculate the F-score for each cluster. So we adjust the predictor label based on the rule. For example, if most KPIs in cluster belong to type A, then every KPI in this cluster is labeled as type A. The final F-score is the average F-score of all clusters. For trend prediction, we use weighted MAP and coverage to measure the error performance. As shown in Figure 6, our TPC has similar NMI results with ROCKA on 3 public datasets. Because the 3 datasets have simple data and few noises, density radius estimation method in ROCKA achieves good density radius and clustering result, and our method also could achieve a similar density radius, so there is no obviously improvement. As shown in the figure, the result indicates our TPC outperforms ROCKA. We find that our ROCKA has relatively low F-score, while TPC obtains the maximum F-score. By plotting distribution figure, we know that KPIs in DS1 has complex figures, and there is no obvious flat part on the k-distance curve of KPI data. Therefore, the best density radius of ROCKA might not be from flat part, while TPC obtains a better density radius from flat part. So TPC obtains a better density radius and then obtains the maximum F-score. Because improved ROCKA adds some more process, so we compare clustering time. According to the result, TPC has similar clustering time with ROCKA. Table 5 shows the trend prediction result. After clustering, 60 KPIs of DUS1 are clustered into ABC. 6 KPIs of DS2 are clustered into DE. TPC has the similar prediction error with AutoPA for DB, but spends much less time than AutoPA for DB. This result indicates TPC is effective and could be used to predict a trend of large-scale KPIs. Table 6 shows trend prediction result on KPIs in C of DS1. C has 6 KPIs. This table has the same result with table 5. In conclusions, we propose a rapid trend prediction framework TPC for large-scale KPIs of cloud databases. And then we propose an improved ROCKA clustering method. Lastly, we conducted comparison experiments on 3 public datasets and 2 industrial datasets. Our evaluation shows that TPC could reduce trend prediction modeling time significantly with less prediction WMC loss, and improved ROCKA significantly outperforms original ROCKA for complicated KPIs. Any comments and suggestions are appreciated. Thanks.